This next section is on impulse, and an impulse is basically just a product of the external force. So if I push on something for a certain amount of time, I would get an impulse on that object, and it results in a change of momentum of a particle or a system. So this is the symbol for impulse. It's J instead of I. I typically we use for current, so we won't use I here. We're going to use J instead. Force is just F and time is T. We can also say that the impulse is equal to the change of momentum. So if you set the two equal to each other, force times time is equal to the change of momentum. The units we use are Newton times a second, not Newton per second, but Newton times a second, or you could use a kilogram meter per second, and that's the same thing that you would use for momentum. Here we go again. This one is they want to know the magnitude of the momentum change, and then they want to know the change in the magnitude of momentum. And so whenever you have a baseball player hit the ball, usually you have a pretty high magnitude and you have a very short duration for impulse. And so let's say that this ball is coming in and it's going at 90 meters per second, and the ball has a mass of 1 kilogram. If it's going in the other direction, we'll say that this is 90 meters per second times 1 kilogram. We'll call this negative 90. We'll call this one positive 90. So if we figure out what the magnitude of the momentum change would be, we know the change in momentum would be equal to, let's do the final first, so this would be 1 times 90 minus, and then we're going to do 1 times negative 90, and we end up with a 180 kilogram meter per second change. So that would be the magnitude of the momentum change. If we look at it just strictly, what is the final momentum and what is the initial momentum of the ball, and we go through and do that, we end up with, we have 90 here, and we also have 90 here. So that is the magnitude. Notice there's no direction there. What is the change in magnitude of the momentum? That would not be any different. You wouldn't have anything there. So this one is much higher. Okay, this one essentially is 180. This one essentially you could say there's no change in the magnitude of the momentum. So that one can be pretty difficult to go through and grasp. You just have to be careful with your definitions. The impulse, when we look at a graph, remember impulse is just equal to force times time. Here's our force. Here's our time, so we would need to find the area under the curve. You could either calculate that using trying to do that for this triangle, so you could separate it into two and then sum the two, or you could just use integration, which is a calculus-based method of finding the area under a curve. On the next slide, we have just an example problem. This is a pretty simple example problem to do. You have a 1.5 kilogram brick. It's dropped on a glass tabletop from a height of 20 centimeters. We want everything in meters, so we're going to call that 0.2 meters. They want to know what is the magnitude and the direction of the impulse necessary to stop the brick. Let's go back to our kinematics equations. We can say that the final speed squared here is equal to the original speed squared plus 2 times the acceleration times the distance. So our final speed here would be equal to the square root of 0 is our initial speed. We will take that and add to it 2 times 10 because our acceleration is gravity, and then we need to put into this 0.2. When you're done, you'll end up with the square root of 4, and that's equal to 2 meters per second. So there's our final speed. We know that impulse is equal to force times time, which is equal to mass times the change in velocity. We're going to look at this part. The mass is 1.5 kilograms, and our change in velocity will go from our final velocity is 0 minus, and here we can say that this is 2 meters per second. So our mass times change in velocity will give us 3 newtons times a second, and because it's negative, it's got to be in the opposite direction, so it'd be upwards. And that is the end of problem letter A. Let's look at B. For letter B, it says if the tabletop doesn't shatter and stops the brick in 0.01 seconds, what is the average force that it has to exert on the brick for that to happen? Once again, we know that F times T is equal to the change in mass times velocity, or you could just say F times T is equal to impulse, same thing. Here we're going to say that the force is equal to the impulse, just rearranging this equation, the impulse over the time of impact. We know the impulse, or the change in momentum, was 30 newtons times a second divided by that 0.01 seconds. Our seconds cross off, and we're left with a force, and that force is 300 newtons. So that is the force that is exerted on the brick. The very next question then finishes this problem, and it says, what is the average force that the brick exerts on the tabletop during this period? And because of Newton's third law, we would just say that it's negative 300 newtons, and that is the end of that section.